So it's a pleasure to have Brad Kinsey here, who is a professor and chair of the Mechanical Engineering Department and professor in the Materials Science program at the University of New Hampshire. He received his bachelor's degree from the University of Michigan and his master's and doctoral degrees from Northwestern University in 2001, and all in mechanical engineering. His awards include a career award from the NSF, the UNH Assistant Professor of the Year Award, the Ralph Teeter Award from the Society of Automotive Engineers, and has been named a Fellow of the American Society of Mechanical Engineers and the Society of Manufacturing Engineers. In 2013, he was the Assistant Director for Research Partnerships in the Advanced Manufacturing Office at the DOE, and the DOE representative to the Advanced Manufacturing National Program Offices. His research interests are in the area of mechanics, materials, manufacturing innovations for metal deformation processes, including control of deformation paths, high-rate forming, impact welding, microforming, and electrically assisted forming. So it's a pleasure to have him here today. His title of his talk is Investigations of a High-Velocity Impact Welding and Forming of Metals. So please welcome him. Thank you.
Yeah, I think this is, can everybody hear me all right? Well, thank you for the kind introduction, and thank you all for coming today. It was a little bit, I was supposed to arrive yesterday when the storm hit, and I was supposed to spend the evening, but instead I drove over this morning, so not too bad of a drive, a little slower than expected, but thank you all as we all still dig out and get ready for the cold of the weekend. So thank you for the introduction. Again, the title of my presentation is this idea of investigation of high-velocity impact welding and forming. And so I want to give context to that. And I was commenting, one of the things we have a seminar series at our university as well, and we have external speakers, but we also have graduate students present to their fellow graduate students, their peers, and one of the things we always harp on them about is giving some context to it. So I'll try to give some context to what I'll be talking about today. So if you go back to the 1970s, if you look at the an automotive body, it was made up of mild steel components, and that was what was used. And so joining of mild steel was easy to achieve. And so if you think about it in terms of, an automobile today, now we do not have just mild steel as a component. We have advanced high-strength steel, aluminum alloys. There could even be magnesium is another material of interest for the automotive industry. So the question becomes then, when you have now this multi-material system, how are you going to join that material together? And so what I'll be talking about today in one of the areas, and this is the welding part of it, is magnetic pulse welding or some kind of high-impact welding process. So what these are images of is some different components where you join multi-material systems together. So in particular, maybe for an automotive application, maybe you want to have a lightweight aluminum shaft, but then you want to have a knuckle that's made of steel, and how are you going to join those two materials together when you can't fusion weld them together because of the difference in melting temperature between the two materials, or because you're going to get poor intermetallics that could cause a failure in the end component. So you need to join them together. Or there's some other applications. This is actually something from a printer or even a biomedical case, but you have this need for multi-material joining. And so then that's where eventually I'll get to with respect to the talk that I'm going to be giving and the process that I'm going to be talking about. And before I get there, I'll talk about it in terms in general, and you'll see as the introduction in my research background, I deal a lot with metal deformation processes. And so what we'll be looking at is high-rate forming of materials. And so one way to get to a high-rate forming process, and what we use in one of the techniques in my lab, is using electromagnetic. So typically in metal forming, you'd have a punch with a given geometry that would come down and form a shape that would then take on that shape of that punch. Alternative to that, and that's just pressure and pushing on it, and that could be mechanical, hydraulic. Alternative to that, you can actually use a magnetic field in order to form a workpiece. So you charge up a capacitor bank with a fair amount of energy. It could be tens to hundreds of kilojoules of energy. You dissipate that into a coil, and the coil could be as simple as a wound wire coil, or we have some industrial-grade coils within our lab. You induce eddy currents, and then you dissipate the energy in the capacitor bank into this. the entire process is pretty quick. You have tens of kilojoules again going, passing hundreds of kiloamps of energy through the wire. You create the magnetic field, and that has a sinusoid, and I'll show some of the current traces in a little bit. The whole process is done within 100 microseconds, but that magnetic field induces eddy currents in any nearby conductive material, which flow in the opposite direction. And then that creates its own magnetic field that then those two opposing magnetic fields create Lorenz forces that then deform the workpiece. And so I think I've hit all of the things that are stated on this. I'll pass around these. What I have here is I'll pass around a quarter, and then I'll pass around two shrunken quarters. And so literally what we do in our lab is we would embed the quarter inside the coil, create the magnetic field. Depending on the energy level that we put through the workpiece, we can shrink down the quarter. So you can see, and if you tilt it just right, you can still see George's face on the quarter, even though it's shrunken down to, the diameter is under half the size that it currently was. So this is a process that you can use to then take a material that's less deformable and get some good deformation out of it. Or as you'll see, in going back to my last slide, you can take that high velocity forming, the fact that material is moving at hundreds of meters per second, and you can use that in order to create a solid state weld. I'll stick with it, and this is just an image from Glenn Dane's group, so you can see that, the amount of deformation. So this is just a aluminum 61 alloy. You can see the amount of deformation that's able to be achieved in each of these images is 30 microseconds apart. You can see the high rate aspect of the process. More work out of Glenn Dane's group showing the types of things that you can do with this process as you create micro features and parts with respect to it. And one of the aspects that I want to talk about is in terms of just the physics of the process. So again, I commented that you create this magnetic field. It's inducing eddy currents in a nearby conductive material. Those eddy currents are only flowing through the outer skin of the conductive material. And so what you have is you can calculate a skin depth of it, which is really just based on if you look at the parameters here, it's the electrical resistance, permeability, frequency of the current trace that you have, and you create the skin depth. And one of the things, what I'll talk about is a lot of doing this with respect to sheet metal. And what they've talked about in the literature is how thick your material has to be in relation to that skin depth in order to get an efficient process. So what in the literature prior to, and you'll see that we refute this a little bit with research that we had conducted, they had said that you need a skin depth much greater than what we talked about is an alpha ratio here, which is the thickness to the skin depth ratio. So they would say that you need at least the skin depth to be half the thickness in order for the process to be efficient. And so we'll look at that as we go through the talk. But again, you can create micro features with respect to the part. Or then going back to that first slide that I had, creating magnetic pulse welds, is if you take a tube and a shaft and you, again, take the coil, put it around a workpiece, and then shrink wrap, in essence, a tube onto a shaft, you can create a solid state weld. And I'll pass this around. You can tug on it. You're not going to be able to separate it. And you create welds that are as strong as the base material. Again, if you have these dissimilar materials, you would not have that be the case. Here, I'll pass around the coil too. That's very exciting, but we'll send that along. I'll say that I was really happy to give a talk where I was actually driving to it. Often I'm getting on planes and I don't take work pieces with me because you don't want to go through security with metal parts, because then questions get asked and you lose samples. Anyway, so you'd take a coil, you'd again have your tube that would be larger than the shaft, but then you would accelerate the tube towards the stationary shaft and create a solid state weld. And what actually happens is you have the materials hitting and sliding with respect to each other, and that's what creates the solid state weld. You can actually see you get a nice wavy pattern at the interface between the two materials as well from that. And what we've shown also in our research, I won't talk about this today, but there's actually a Kelvin-Helmholtz shear instability that occurs as the two materials are moving relative with respect to each other, and that's what creates the weld. I'll say there's other ways that create these high velocity processes. you can do explosive forming instead, where you literally have a detonation that creates a shock wave, and you often do this in water, and then that shock wave is what deforms the material. This process, a lot of the high rate forming comes from the Cold War when they were trying to create missile cones, and this became a way that you could get a lot of deformation in the material to create the shape desired. Or you can do, and again, I'll show this a little bit, some results from vaporizing foil. So as opposed to having a magnetic field that gets generated, you actually can take a foil of material, say aluminum, and vaporize it and create a plasma. And from that plasma becomes the driving force for the deformation in the process. And so some of the benefits with respect to this impact welding is you can join dissimilar materials, you're affecting the heat affected zone, making it smaller, and then also the high production rates that occur. And this just shows some more images of parts or different material systems that can be joined. Here's copper and aluminum, copper and brass, just aluminum to aluminum. You can sometimes see little vortices that get generated with respect to the weld. And again, you need a certain velocity with respect to the process. And there's a certain amplitude and wavelength with respect to the welds that you typically see in these interfaces. So the research questions we were really after was, because velocity is such a key in the process, can we come up with ways to analytically predict the velocity during these electromagnetic forming processes? We also looked at what the fundamental physical mechanisms were, and then I'll end by talking about some process parameter ranges in which you can achieve the good solid-state welds in the process. So I really already went over an overview of the process. I'll talk about that velocity prediction and experimental validation, and I'll talk about it with respect to two processes. One is just electromagnetic forming and axisymmetric tube compression. So for both of these, I'm really just accelerating the material, measuring the velocity within the process, because that's a key process parameter. And then we'll go on and talk about some numerical simulations of a weldability window to talk about what range of parameters, again, velocity, and the other key parameter is with respect to the impact angle. How are the two materials colliding with respect to each other? That becomes the other key process parameter to consider. So again, when I talk about electromagnetic forming, I'm going to talk about a specific tooling geometry with respect to that. And they talk about this as being the uniform pressure actuator. And this, again, came out of Glenn Dane's group at Ohio State, where, again, they would have a coil that's creating the magnetic field. And one of the things you want to do within the process is really control where the current is flowing as it's getting induced in any nearby conductive materials. And so what they worked on was having this return path that goes around and then through a die and back around, so that you create a nice flow of the induced eddy currents in the workpiece that's there. And this die, when you form it into a die that has a certain feature, those were those microscale features that I showed Glenn Dane's group being able to create with this process. But you can also replace this with just free forming of the material into space. And so this just shows some images of the return path and the coil that they created, and then they pop the two together in order to create it. And so, some of the advantages is it becomes a really efficient process in order to, again, control where the currents are flowing, create a nice uniform pressure distribution. I'll show some of the pressure distribution curves that we had analytically predicted as well, and it's pretty efficient, robust coil geometry. So again, what we're after with respect to this is really trying to predict that velocity within the process. And so we're doing electromagnetic, mechanical, analytical model. And we've done numerical simulations, and certain numerical simulation software packages allow you to do those all coupled together as well. But we're looking for maybe a more a simplistic way to look at it. Could we really do the predictions? So, these are all loosely coupled together, where you start off, we figure out the coil parameters, we send a certain current trace into the workpiece, we create a magnetic field, that generates a magnetic pressure. We started off with respect to doing this where we just assumed rigid body motion. I'll show an extension of this where we got rid of that pretty simplistic assumption, but we wanted to see could we just simply predict it with rigid body motion? So then from that, we have acceleration and workpiece velocity. And you could also use this in order to design a coil. And the final thing, you'd get position, and it's loosely coupled because the workpiece moves. And when the workpiece moves, that changes the magnetic field that gets generated in the process. And then you have your current trace changing and the current level changing. And so you need to keep track of all of this with respect to time. So I'll go quickly through the equations, not spending too much time on them with respect to all the different steps within the process. So, for the electrical analysis, very simple circuit design where you'd have the capacitance, resistance, and inductance of the circuit. You'd be able to, and I'll have numbers later on where we can measure it with respect to the machine, with respect to the coil, keep track of all of that. This just shows the idea of the circuit where you have this electromagnetic forming machine. Again, charge up capacitor bank, close a switch, send it through the coil. You have some efficiency losses when you create the magnetic field. That's the coupling coefficient. And so we measure the coupling coefficient. I'll show you how we did that in a little bit. And then, again, you have the current flowing through the workpiece, which has its own resistance and inductance as well. And so that becomes the way that the electrical analysis works. This just shows, out of the electrical analysis, what we're able to predict with respect to the process. Here's the coil parameters. Here's for a discharge of 12 kilojoules. The rise time is 30 microseconds. Again, this process occurs very quickly, and the peak current in that process is 135 killiamps. And what you can see here is not only current, but voltage with respect to time. And this shows from experiments what we predict analytically as well when we do the equations on the previous slide. We do, that first peak captured pretty well. Later on, as the workpiece is moving, as things are changing within the electrical circuit, as things are heating up, which we don't account for, you start to lose the accuracy a little bit. But you'll see later on that it's really this first peak of current that does most of the deformation in the process. Feel free, by the way, at any time to stop and ask questions. This doesn't have to be something that you wait. If you have a pressing question, please don't wait until the end. Shout it out. So then we go from the electrical predictions to the magnetic predictions, the next step of the process. And so we have the current flowing through the process, the current density, the J, and we're going to cross it with the magnetic flux density in order to create the value of the forming force within the process. And to do that, you really need this magnetic field, which the magnetic field, this is the side view of that, of the uniform pressure actuator. This is that return path. Here's a 6-turn coil. Here's the workpiece. And just to say that we have a coil and we discretize it into dx, dy. We keep track of all the locations of the magnetic magnetic field with respect to that for all the different coils, and then we just use all of that in order to sum up the magnetic field at a given location within the workpiece. And this was Alessani's model is the one we used with respect to that. And so from that magnetic field that gets generated, what we get is a magnetic pressure. And in order to do that, then you have your magnetic pressure really as a function of that magnetic field. This is where you throw in your coupling coefficient, the permeability, free space. And then again, one of the things that we had, which is a real limitation, and I'll show some more recent results where we've addressed this and gotten rid of this rigid body motion assumption. But otherwise, we just use F equals ma in order to determine, with respect to that forming force from that pressure, what is the acceleration of that workpiece, and from the acceleration we get the velocity that we're really interested in the process. So what this shows is the results from the magnetic part of that analysis. You can see here pressure versus time with respect to x or along the length. And so what you see here is here's the 6-turn coil, and you can see how there's these small bumps with respect to the pressure within the process. And so obviously those bumps are coinciding with the pressure being the magnetic field, and thus the magnetic pressure being a little bit larger where those coil locations are. And then you can also see here after that first peak, there is other peaks, second and third peaks, that do occur because of the current trace oscillating within the process. And that's what you see here as well, is there's the current oscillating, there's the pressure oscillating going up and down with respect to the fact that you do have that current trace that's changing. But you are moving the workpiece again in the process. So what you see here is a fast acceleration. This is a velocity measurement. Fast acceleration plateaus out when the current goes down, the pressure goes down, accelerates up again, plateaus, accelerates up. And again, we're just doing rigid body motion, so it's never slowing down. It just continues to move, which is an assumption within the model. What you'll see is we're really after kind of capturing, do we get that first initial peak velocity, or that plateau in the velocity that occurs. So we have so that's the analytical model. What we want to do is compare that to experimental results. So what we have here is the construction of our uniform pressure actuator. So this kind of shows the entire setup flipped around a little bit compared to what I had before. So here's that return path, the workpiece, our 6-turn coil, which is shown here with the leads brazed on. This is kind of a side view with respect to that. We use photon Doppler velocimetry in order to measure the velocity in the process. So that's a laser-based system in order to measure velocity. I think I have that on a later slide, so I'll say more about that. But this shows it all kind of clamped together and what we'd be putting into a process. And we'd be hooking up these leads to that capacitor bank that we have in our lab. And this just shows the chamber that we do with respect to, so this is a forming box where we do all of our experiments so that we have a little bit of protection going on. We put a Rogowski coil, which is what measures that current trace within the process. And then we use, again, I had mentioned photon Doppler velocimetry to measure the velocity of the workpiece. So the way that system works is it sends out a laser pulse that hits the workpiece, gets reflected back. You'll always see on our workpieces we have photoreflective tape in order to make sure that the return of the laser beam out gets back to the detector well. And what's maybe not clear here is there's a little hole within this top plate that we're able to look through with the laser beam. So that's the way that we measure velocity in the process. The laser beam goes out, returns back as the workpiece moves. There's a shift or a beat frequency with respect to that laser pulse, and that's what we're using to measure the velocity in the process. And so what this shows is, again, one of the key parameters is with respect to that coupling with respect to the process. So we want to understand how much of that electrical energy got captured within the process. So what we did in order to do that is we bent up a specimen so we could use our Rogowski coil in order to measure the current passing through the workpiece. That's how we were able to calculate a coupling coefficient for our process, which is about 0.45 with respect to it. And we just measured the primary and then the induced, and the induced is as a transformer effect because of the multiple coils that are within the process. So this shows some deformed work pieces as well as that current trace. And I put the current trace back up here in order to show kind of the shape of the workpiece. So what we did was we were just deforming 6061 T6 aluminum material. We did 3 different energy levels, 3.6, 6, and 8.4 kilojoules. And you can see the amount of deformation that changes. Here's the original workpiece and the amount of deformation that occurs with the different energy levels. And you can also see why we talk about it as being a uniform pressure actuator. It's not completely uniform. You get this saddle shape with respect to the process. One of the things we're doing right now is running some numerical simulations that do predict that shape as well. And so we're going to be able to look into a little bit more why that physically occurs within the process. And this shows predictions of the velocity compared to our analytical model. Again, what we're really interested in is that first plateau effect within the process. So here's the 3.6, the 6, and the 8.4 kilojoules of current release. Experimental measurements, we did 3 runs of each experiment. So you can see really consistent velocity measurements with respect to the velocity measurements. And then you can see how we're doing pretty well predicting analytically despite the fact that we had that very simplistic rigid body motion assumption, but I'll show in a little bit the way that we could address that in reality. So decent predictions, again, the coupling coefficient being a parameter that's going into our model. So we can see here that that coupling coefficient is the same regardless of the energy level put in. And so what we wanted to do is look at it in terms of I had talked about that alpha ratio, which is the sheet thickness to the skin depth calculation. So eventually you're not going to be capturing the electrical energy. You're not going to be inducing the eddy currents properly in the workpiece. And as you do that, what you're going to see is then that you're not going to be predicting well, or that coupling coefficient is going to be changing. And that's what we're looking for, is at what level does that change occur. So the way that we did it, the first way that we did it is look at different thicknesses of the workpiece. So it's always the thickness of the workpiece to the skin depth. The skin depth stays constant regardless of the thickness of the material. So we could take 2 millimeter, 1 millimeter, and 0.5 millimeter materials, and we could change the alpha value using that. And you can see here for 2 millimeter and 1 millimeter materials, we capture it well with respect to that first plateau. I talk about the first plateau because it becomes more difficult after that in order for the analytical model to capture it. So we really are looking at it in terms of that first plateau region. What you see here for the 0.5 millimeter material, we stop predicting it well, or what that means is we're not inducing the eddy currents well. That 0.45 coupling coefficient is not the correct value to be using, and so we stopped being able to do it. So at least compared to previous research where they were saying, oh, you needed a value of 1.5 to 2, this shows, these tests show that 1.1 seems to capture it. And then what we also did is not just look at the one material, because the skin depth is really a material parameter. We're able to do different materials and look at it in terms of changing the coupling coefficient, or the skin depth with respect to that. So we took pretty pure copper or some brass alloys or stainless steel. We looked at the resistivity. We note the density differences between them as well, and the conductivity differences, and so stainless steel not being a very conductive material. And then we're able, again, to get some different alpha values that then we can evaluate the alpha value as far as the efficiency of the process. So this shows the results of that for the different materials. So you can see here through the first plateau, we're able to predict well the velocity for a number of the materials. Start to lose a little bit here for this particular copper alloy, and definitely do not predict well for the stainless steel. So again, thinking about that alpha value, thinking about what kind of ratio you need between the thickness and that skin depth. Now we're down to maybe even a 0.66 is able to fairly well capture that effect. And all of these were 1 millimeter material at the 6 kilojoule level. And so as I said, that all included a rigid body motion assumption, not a great assumption for mechanical deformation. So what we've gone on to do recently, and we're still working on this, so it was easier for me to present all the data that we had from the rigid body motion assumption, because that was more of a complete study. But what we can also do is look at simple plate theory. Again, wanting to have a very simplistic analytical model in order to evaluate the process. So we can use Mendel's plate theory. Here's the equations where you have normal terms with respect to the stress and the strain in the process, shear terms, shear strain being calculated by not only deflection but rotation. But what you can see here, if I go on to the next slide, and then I think the other thing that's nice about doing the plate theory is you can see the saddle shape, hopefully, with respect to this 3D point plot. But before, when I was presenting the other results, and maybe I should have been more clear about this, that really wasn't capturing any kind of shape change. It was only capturing, the velocity at a point right in the center. And so what we can do now also is we can look at the velocity, and we still are reasonably predicting the velocity within the process. But with the other thing that we can look at is in terms of predicting the shape of the final workpiece. So this is the width direction. So this is the length direction. This is where you'd have the 6 coils. And so you see that saddle shape. So you can see we're able to predict pretty well the center of the workpiece. We lose it at the edges. Part of the reason, I think, is because we actually had unclamped the specimen. So when we're redoing some experiments now, we'll keep the specimen clamped while we do the measurements. That may help to address this a little bit as well. But I think we are missing a little bit of the nuances of this, and so we'll be using finite element simulations in order to investigate that a little bit. But you can see also a good agreement with respect to the width direction of the process. So that's all with respect to the uniform pressure actuator or sheet forming. I'll show some real quick slides where just showing the same type of principle used for tube compression. So if you think about the shaft to the tube welding, this is again where we'd really care about the velocity within the process. And so this again just shows the setup. This is just another schematic of the idea of having the capacitor bank that goes through a high energy switch. What becomes important is having some type of way to concentrate the electrical energy. And so you'll often have field shapers within the process that concentrate the energy over a small landing area. So you'll see that. Otherwise, this maybe shows a little bit more of the process setup with the high rate oscilloscope, the photon Doppler velocimetry system, and this is the commercial coil we use for these processes. This is kind of a side view of what we have in the process. So this is a 4-turn coil now, and what this component is the field shaper. Again, you have the coil, but you want to concentrate the electrical energy or the magnetic pressure down onto a smaller area. So you use the field shaper in order to do that. And again, with respect to skin depth, the induced eddy currents are on the outside of the workpiece, but then what you have is, as it goes through here, and you have a little slot in the coil that will focus the energy down into that landing area so that you can have the deformation over a smaller area compared to the larger area, focus it down. But this shows the overall dimensions of the entire process with respect to the tube and the axis of symmetry, and again, that field shaper. And so all of this will be with respect to a 2D analysis. So we're just looking at a cross-section here. Getting the velocity measurements, eventually you'll see, similar to what I did for the sheet forming, we'll have velocity measurements that we'll compare our analytical model to. And so getting the velocity measurements out of a tube compression is a little bit trickier because we really don't want to cut through the coil in order to look at the velocity of the tube on the outside. So what we do is we actually create a workpiece with a 45-degree mirror on it that we pass the laser beam down, reflect it off the 45-degree mirror, reflect it back out, so that way we're able to get velocity measurements with respect to tube compression as well. And so otherwise, I'm going to be doing something pretty similar to what I had last time as far as the model itself, where again we have this electrical component, the magnetic component, field, and pressure, and now we're able to do some plastic hardening, keep track of the plastic hardening with respect to the workpiece. Others have done some analytical modeling where they didn't really keep track of the work hardening of the material, the plastic deformation, so that's an added benefit to the research. What you see here again is that idea of a current trace as well as the voltage within the process for the electrical. I already showed the equations previously. And you can see here a much different pressure distribution when you have this coil, the field shaper within the process. It really does focus down the electrical energy well in the sense that you get this higher first peak and then not so much as far as the second and third peaks, again, despite the fact that you have the current trace diminishing. For the magnetic process, or for the mechanical process, this became the way that we solved it. Again, we're looking for really simple mechanical models. So we just use simple tube equations with respect to the longitudinal and hoop stresses that occur within the process using very simple von Mises-Yale criterion. We did some Kolsky bar tests in order to determine the properties with respect to the high rate forming. Made some assumptions within the process, but we're able to calculate the hoop strain within the process. And from the hoop strain, then we're able to determine the velocity within the process. So here's the results of that, where you can see, again, we're able to, these are experimental results, two energy levels, 2.4 and 3.6. If you actually go much higher than that, you can start to see you have some wrinkling within the tube, so it compresses down too much. And then our analytical model is doing pretty well predicting the peak value. There's a little bit of a time delay shift, likely due to the incremental aspect of our modeling efforts. But I'll say that all of this was two-dimensional in nature as far as the prediction. And so we are running, again, FEA simulations. LS Dyna has a nice package where you can do the electromagnetic and mechanical simulations of the process. You can actually, I'd commented on the field shapers having a slot with respect to for the geometry in order to concentrate the electrical energy down. You can see that with respect to, this is a formed workpiece, and so you'd be looking at it in terms of the full 3D effect versus only 2D. I didn't plot in the end because I didn't talk enough about the numerical simulations, but we actually get good prediction out of the numerical simulations as well. And that's the velocity, and then with respect to displacement, again, good prediction with respect to the analytical model to the experimental results. So I'll do a little bit of a summary with respect to this idea of predicting velocity within the process. Again, we're looking at velocity because it's such a key element of the these high impact welds. And I think we've shown that we can have these pretty simplistic models, analytical models that capture the effects well. Again, we've done numerical simulations in FEA software packages. It takes a little more time to set up, a little more difficult to implement, and so we can show that we have some good ability to do some predictions despite the simplicity of the analytical models. And I'll also say one of the other findings of it is, really thinking about that, how much that ratio of thickness to skin depth needs to be in order to get a successful inducing of the eddy currents and a successful process. So what I want to do now is go on and talk a little bit about some more numerical simulations and some more experiments, but with respect to actually creating welds. And so with respect to it, there's different algorithms with respect to numerical modeling, and so we've looked at a number of them. If you just use what traditionally is used, pure Lagrangian, you get a lot of element distortion at the interface because of so much shear deformation occurring as the materials are moving with respect to each other. So we found, and we've done all of these different ways. What I'll present today is kind of arbitrary Lagrangian Eulerian simulation ALE, which is an adaptive message, so you have a different mesh right at the interface in order to address the fact of those large deformations. But you can also do pure Eulerian or even smooth particle hydrodynamics in order to run a simulation and capture the effects. So this just shows a little bit of information with respect to our model. Again, the other key process parameter in addition to velocity that you'll see us varying with respect to this is just the collision angle. As the two materials come together, what's that angle that they're coming together at to create that sliding motion? And so what we did initially was just very simple 2D models where we would set some impact angle, we give it an initial impact velocity, and then again we have at the interface, we have the ALE elements that are going to be able to adapt to handle the large energy distortion within the process, but otherwise, the rest of the mesh can be a regular Lagrangian in order to speed up the simulation time. And those become the two parameters that we're looking to vary is that impact velocity and the angle between it. I should have said for the other work that we've done, that when you're doing this high rate deformation and you're inducing eddy currents in itself, you are heating up the workpiece, and that does affect the material properties. And so you saw in some of the earlier models, we weren't accounting for that. But here we are in the sense that we are able to, again, do some Kolsky bar tests so that we have a sense of the temperature that's being implemented into the numerical simulations as well. So we use a Johnson-Cook model for that. And so this just is the nice thing about numerical simulations and why I'm anxious to look at the numerical simulation results for the other cases that I was talking about is because then you can get a lot more information out of it. You can look at the shear velocity at the interface and see what the shear velocity is. And so what we found is when we have a wavy pattern, you can see the wavy pattern here with respect to the welding of these two materials. This is just aluminum to aluminum welding. But you get this nice uniform shear pattern. If you are at a given impact angle velocity that you don't see a wavy pattern, you don't see this nice symmetry between that, and you don't see nice symmetry between the shear stress at that interface. But the other thing that we'll be able to look at is then the temperature rise at the interface. And again, the nice thing about the numerical simulations, we can have some sense of that, and you'll see we do an attempt at comparing the temperatures at that interface by looking at micrographs of the material. This idea of a weldability window, again, it's really collision velocity versus angle of collision. And so people have looked at this as far as a weldability window where you're able to get a nice wavy interface pattern. Again, I had talked about early on about having this wavy pattern, which may or may not be necessary for a good weld, but definitely if you have that wavy pattern, it is an indication that you have maybe achieved a good weld within the process. And so what we did was varied the impact velocity, varied the impact angle as we had talked about. And then what you can do is then do a bunch of simulations. And this is one of the things the graduate students asked me at lunch today if I had any advice. And I commented that you should always be interfacing with your advisor often. This is what happens when you don't interface with your advisor often. My graduate student ran all of these numerical simulations. The numerical simulations were taking a couple days to run, but he was about halfway through before we met up and he told me what he was working on. And I was like, I don't know if that would have been my first idea. But he did. He ran a large number of numerical simulations. And then we could really look at the numerical simulations and look to see regions where there is no bond. And so sometimes the materials would hit and they'd actually rebound off each other in the simulations. And I'll show where we actually see that in some other numerical simulations. And this kind of shows that idea of a smooth interface where you see all the shear velocity or the shear deformation or shear stresses on one side of the interface, not the other. And then you have a good, nice, symmetric shear velocity profile. And you could sit there and characterize them. And you could also look at the temperature and compare the temperature to the melt temperature of the material and see where you might have a good weld with respect to it, but you also might have an area where you have some potential for melting of the material because you're at temperatures much above the workpiece or the melting temperature of the workpiece material. And so we talk about these as regions 1 and region 2. And again, going back to that weldability window I showed previously, we can actually then map onto it. And we saw what we expected to see even in the numerical simulations where there's going to be cases where there's no bonding. And then you're going to see some cases where there's a straight interface. And then there's going to be cases where you see a nice wavy pattern that gets created and some where the temperature is so high that the material is melting. So it's very consistent with what other people have found with respect to this experimentally. And again, I think what the last bullet here talks about is the fact that the problem with melting is that you can have these intermetallics which could lead to failure within the sample in use. And so what we wanted to do is then run some experiments to kind of validate our numerical simulations. And so what we used was the vaporizing foil because you can create the much higher velocities than you can do just with the magnetic fields that get generated. So again, what you have is and I think the next slide will show this a little bit better, but you create a plasma by vaporizing a foil in order to create it. So I think this actually shows probably a better view of this, where you can see the experimental setup here, where here's the foil, the workpiece is here. Maybe I'll start pointing to this one. Here's the workpiece. You have these standoffs that are going to change that impact angle, and you have your vaporizing foil that one end is connected to one lead of the capacitor bank, the other one's the other. So it's really using the same capacitor bank that you use for electromagnetic forming, but now you're just vaporizing the foil instead of passing the current through the coil and creating a magnetic field. And you just use a thin foil of aluminum, for instance. And what you see here is, again, changing the standoff distance. So standoffs are a little bit closer. You get a higher impact angle. As you move them farther away, you change the impact angle in the process. And if you have too low of an impact angle and 3 degrees isn't enough in order to create a weld, you actually get this racetrack where the materials have hit and are sliding with respect to each other, but welding does not occur. And so what we did was we looked at 3 cases, and so we just took 3 of the tests in different regions. So one where we're down here, experiment 1, where we should see a wavy pattern, one where we should see some melting with respect to the material, and another one, even a higher test, where we should see some melting with respect to the material. And so this shows that test 1, again, should be seeing a nice wavy pattern. This is what you see at the interface along the entire interface. So with respect to the plate-to-plate welding, the plates are hitting and they are sliding with respect to each other. A little bit different, though, than just the orientation where I show in the original simulations where there's just an edge hitting and then the impact angle and the material sliding. This is coming down flat, hitting, and where it hits in the center, you actually don't get a weld. You actually get a rebound of the material. So this is an unbonded region. But then as it hits in the center and then moves in both directions, you'll get the correct sliding, the correct impact angle and velocity and the collision velocity in order to kick up the wavy pattern. So you can see the wavy pattern start and grow and then dissipate out. And what we're able to do is, so this is micrographs strung together over that interface, and then you can start to zoom in and look, and you'll see features like voids within the microcracks or elongated grains that occur with respect to the process. So again, this is, would be deemed a nice weld because it's got a wavy pattern that doesn't indicate any melting. And again, this was something that didn't indicate any high temperatures or temperatures so high that you would get melting in the simulation. Here we show that end-bonded area, so you do see a gap within the parts when you look at them. But even when you have a gap, you can start to see some high temperature or some features that, I put this in because Ian, I know, would want to have some micrographs, right, Ian? So he can help me interpret these a little bit better. But then you can see some effects within the micrograph that could lead you to think that there's melting occurring there. Or if you look at a different region, off where the wave occurs, you can still see some region that maybe is some indication of melting. And then again, here is just the highest impact velocity case, this case 3, where again, right at the interface, you just see these features within the material. Even to the point where you see some gap separation between them. Even on something that seems like a nice wavy pattern, you have some gap that occurs where the materials have hit so hard together. And so, again, the original simulations we had ran were just 2D plate hitting at a point and then sliding. So what this shows is more trying to emulate the process itself. So we'd have some standoff distance. This is numerical simulations, same idea. We're using Abacus for this. And with the ALE elements at the interface colliding together, we're able to figure out what kind of velocity to put in the process, again, from photon Doppler velocimetry. And then this shows the numerical simulation results where you can actually see the wavy pattern get generated as the workpiece comes and interfaces with respect to it. And this is a temperature plot. So again, what we're looking at is temperature to tell us whether or not melting could have been a concern with respect to the process. But the shape, hopefully you can see, the shape is pretty consistent with what we get numerically in the process as well. And again, the nice thing about numerical simulations is then you can go in and look at lots of details with respect to it. You can look at things like the wavelength to amplitude within the process, and you can do that experimentally as well. And you can see some similarities with respect to the numbers. Again, kind of a gap region here within the numerical simulations, but then we're able to get to the wavy patterns, which are pretty similar to the amplitude and the wavelength of the wavy patterns at the interface. And again, with respect to temperature, you can see, even with respect to this, you can see a melt layer temperature that seems to be on the same order as far as the high temperature region within the process. So as far as conclusions, again, velocity is a critical parameter with respect to this impulse welding. And so that became the focus of trying to create those analytical models in order to determine that. We showed that hopefully that ALE is able to actually predict the effects with respect to the process, including a weldability window, and that morphology investigated, with respect to different methods. And so the other thing that I'll point out here is these are the last slide that I had pointed out, the experimental versus FEA amplitude to wavelength. And then we also had our mathematical model and our FEA simulation. So we actually did, and I had mentioned it earlier, the idea of materials hitting, sliding with respect to each other, Kelvin-Helmholtz instability. I didn't talk about it in the presentation today, but those are parameters, or you get some decent consistency with respect to that analytical model and the numerical simulations as well. And so as far as acknowledgement, so there's 3 graduate students who are really responsible for the research that I was presenting: Ethan Thibodeau, Shunyi Zhang, and Ali Nazuri, some funding from the National Science Foundation. And Glenn Dane is someone that I have some joint NSF funding with respect to work on this process, and he's always been great as far as giving some guidance as I've been working on this And so with that, thank you very much for your attention, and I'd be happy to answer any questions.